All right, this is AP BC Calculus. We're doing a BC only unit. This is Unit 10, Section 9, determining absolute or conditional convergence. So the difference between absolute and conditional really just boils down to whether the series would converge if it were entirely positive. So let's look at what I mean by that. As we discussed briefly in 10.7, the basic definition of converging absolutely is that the series converges even if all of its terms are positive. So a series converges conditionally if it only converges because some of the terms are negative. So for example, we know the alternating harmonic series converges because we've seen that, and also because we totally have it memorized. But we also know the regular harmonic series diverges, right? So that means the alternating harmonic series converges conditionally, but not absolutely, because if we had made all of those terms positive, it would diverge, right? So let's go ahead and walk through this. So as you get better at this, you can start to do it without actually doing a lot of tests. I can look at this and realize that it converges absolutely. Here's why. The alternating version converges, right? So the alternating -1 to the n minus 1 has the b sub n term 1 over n squared, right? So this definitely converges as an alternating series because b sub n is decreasing. As the n values get bigger, you're going to get smaller and smaller fractions, and b sub n is approaching 0. So the alternating series converges, but the absolute value of this thing is just this thing, which also converges because it's a p-series, right? Also converges because it's a p-series or p is 2. So this thing converges absolutely. So when I said I can just look at it and say, oh, hey, that converges absolutely, essentially what I'm doing is I'm saying if I ignored the -1, I'd have a 1 over n squared. In my brain, 1 over n squared definitely converges, so this would converge either way. Okay, so now with this one, right, this is an n to the 3/2, right, which is a p that is 3/2, which is bigger than 1. So again, this is going to be one that converges absolutely, because if I look at it, right, so this is definitely going to converge absolutely, right, because this is a p-series that converges. So like 1 over n to the 3/2 would converge, right? So even if there wasn't alternating, so the alternating part converges, right? Because, so the alternating part definitely converges because it's got the -1, which is the part that's alternating, and it's got a b sub n that is 1 over n to the 3/2, which is decreasing and approaching 0. So b sub n is decreasing, b sub n is approaching 0. So the alternating series definitely converges, but it would also converge if it didn't have the -1, so we say converges absolutely. All right, now this one's going to converge conditionally. And again, I can do this because I've done this a bunch of times. But when I look at this, I say, wait a second, this is a -1 to the n plus 1, and then a 1 over n to the 1/2. So this piece, right? So b sub n is decreasing, b sub n is approaching 0. So the alternating series definitely converges. But just 1 over n to the 1/2 is a p-series with p is 1/2. So this diverges. So we would say that this converges conditionally, or conditionally converges. Either one's fine, right? So conditionally converges because, again, without the negative, this thing would converge, right? So this piece diverges, this piece diverges, this piece converges. That's called converging conditionally. All right, so this is a geometric series, right? So this is the piece that says it's alternating, right? There's two ways to do this, right? So one way to do this is to leave it like this and treat it as an alternating series, right? The other way to look at this, actually, if you kind of wanted to cheat, is you could rewrite this, because they're both to the k power, you could rewrite this as a -1/2 to the k, which is just another geometric series, right? So that's geometric where r is -1/2, and since the absolute value of r is less than 1, this thing converges, right? It's going to converge, but notice that this thing also converges, right? So without the alternating, if you just looked at this, then you'd have an r that's a 1/2, and the absolute value of 1/2 is less than 1, so this also converges. So it would converge whether you had the alternating or not. It wouldn't matter. It would converge either way. So this is absolute convergence, or converges absolutely, right? Because it would converge whether you had the negative or not. All right, let's do an E3. Okay, so for this one, The answer is going to be that it diverges. So here's why. If I look at the alternating series, right, the alternating series, I would need my b sub n, which is 1 plus 2 to the k over 3 to the n. I would need to know if that's decreasing, right? And I would need b sub n to be going towards 0. Well, this is the easy way to notice that I have a problem, because the limit as k, oh sorry, it's b sub k, not b sub n here. As k approaches infinity, 1 plus 2k over 3k is going to be a 2/3, which is not 0. So I could actually argue, this thing diverges as an alternating series, right? If it diverges as an alternating series, there's no way you even have to check the positive version, because if even having positive and negative terms was not enough to make this thing a finite sum, then if they're all positive, it would also diverge. So this thing diverges. And essentially, I could cheat and I could basically use the nth term test for divergence, because I could look and say, hey, as k approaches infinity, I don't care about this thing, but this thing is going to, so it doesn't matter if this is negative or positive as k approaches infinity. Like, that doesn't matter, because I'm going to end up getting either a positive or a negative 2/3. Either way, it's not 0, so the thing diverges. All right, so in this one, right, so this one's a little bit different, right? So this is going to be conditional convergence. And again, you get better as you look at it. But so this is the piece that's alternating. So let's first check that the alternating series converges, right? So is k squared over 2 plus k cubed decreasing? And it is. And you can see this if you plug in values. But essentially what's happening is this behaves a lot like... So this is how I was able to look at it and say it converges conditionally. It behaves like a 1 over k, right? Because we always look at just the leading terms. So I say, okay, cool, it's decreasing because I understand that that's how it behaves. Is this thing approaching 0, right? Is b sub k approaching 0? Well, sure enough, if you plugged in infinities, it would behave like this, and the answer is yes. So this thing converges, right? But the question is, would the positive version converge, right? Well, the positive version won't, because I can compare the positive version to 1 over k, right? And either, so I could, or if you wanted, you could compare it to k squared over k cubed plus 2, over k cubed, rather. It doesn't matter. So if I use limit comparison, I would find that the limit as k approaches infinity of k squared over 2 plus k cubed divided by 1 over k is going to be the limit as k approaches infinity of a k cubed over k cubed plus 2, which is a 1, which is a finite number, so they behave the same. So behave the same, which means that this series diverges. Okay, so if it converges as an alternating series but diverges as an all positive series, this is called conditional convergence. Or converges conditionally, either one's fine. So conditional because it diverged when it was all positive. And that is the difference between absolute and conditional convergence.